So very quickly, let's recall what the Pascal lines of a hexagon are, right? So imagine that I have a conic inscribed hexagon. And what I'm going to do here is I'm going to take opposing sides of this hexagon. So here's one side, here's another one, and I'm going to intersect them at a point. And I have three cyclic ways of doing this for the same hexagon, right? So I can take side 1 with side 4, then I get this point. Then I can take side 2 with side 5, and I get this point. And then I can take side 3, the small side over here, with side 6, and I get this point. So when Pascal, Blaise Pascal was about 16 years old, he discovered that if these 6 points are inscribed in a conic, these 3 intersections we just described will be collinear. And we can identify these 3 points here with a line called the Pascal line, right? Now, given 6 points, in general, there's 6 factorial ways of actually there's 6 factorial permutations of those points, but modulo ordering and reverse ordering, sorry, not modulo ordering, but modulo circular rotation of these vertices. So 1, 2, 3, 4, 5, 6 is identical to the sequence 2, 3, 4, 5, 6, 1. I've done a rotation, right? And 1, 2, 3, 4, 5, 6 is also identical to 6, 5, 4, 3, 2, 1. So when you take these 720 possible permutations, which is 6 factorial, and you modulo out these reversals and these cyclic rotations, you end up with 60 possible orderings, right? So given 6 points, there's 60 possible orderings, and there will be 60 possible Pascal lines. So in this page here on Math World, he is going to show some really nifty geometric properties of these Pascal lines for a general hexagon. What I want to do in this video is actually marry Pascal lines with a couple of Poncelet n=6 families. So let's go over to my Mathematica notebook where I'm doing this, which is this one here. So we're going to start with a first family. So this is a family of hexagons, and this is known as the harmonic family. So this is a circle inscribed family which circumscribes a very special inellipse called the Brocardin ellipse. And I'll put some links in the description for more information on these harmonic families, right? And I can actually, there's a one-dimensional family of these. I can actually change the aspect ratio while keeping the circumcircle constant. So I can actually choose a particular harmonic family. Okay, but let's just choose this one. And now I actually, because I have n=6, I'm going to light up the 60 Pascal lines of this family. And I want to show you guys a couple of really interesting and not understood phenomena. Okay, so let me actually pick a family that is going to do something like this. And I'm going to move this to the left. And now you can right away see that there's two areas here where there seem to be a bunch of lines that are congregating. There's this one over here, at some mysterious point, and then there's this one here and this one over here. Well, let's watch this thing in motion. Notice that this first line here, and you can actually safely ignore the flashing in and out of some lines. This means that they're actually going through infinity. Some of these intersections and some of these Pascal choices, they're actually creating two parallel lines, so sometimes I cannot draw them because their intersections are at infinity. So ignore those, but what you can see here that is pretty stable is the fact that there's a first bundle of lines passing through a first mysterious point. That could be, let's actually vary, so let's vary the aspect ratio. Yeah, I don't know what this point is. Maybe this is the Simedian point of my harmonic family. So it looks like there's a bunch of Pascal lines passing through this first point here. And then there's also a line that is vertical. There's a bundle of lines here that is vertical, through which there are two intersections. There's this one. I believe there's only two, right? Let's see. There seems to be only two dynamic intersections. So there's one over here and another one over here. And there's a bundle of lines here. You can see that this line is being drawn thicker. So it means that there's several Pascal lines being overdrawn. And this could be a special axis of the system. For example, the Lemoine axis. These harmonic families, they have both a Simedian point and a Lemoine axis. So I wonder if this congregation of vertical lines and these two sort of macro intersections here could be happening over the lim1 axis of this family. Okay, so two nice phenomena here happening over my harmonic polygons. And I'm sure that there's a bunch of other phenomena that I haven't really checked. You can see here that, for example, it looks like this bundle here is always intersecting at a point on the polygon. Let's see if this is true dynamically. Yeah, so this bundle here is actually intersecting at the contact point of this opposing vertex and Brocardian ellipse. And you can see that this phenomenon repeats over here. There's a bundle of 3 or more rays. So at every contact point, just by symmetry, I would expect, and I don't quite see it here, but I would expect something going right through it. So there's one or more Pascal lines going through the contact points of my harmonic polygon with the caustic. Okay, so this is the first phenomenon. It's the Brocard family. And I want to look at another very interesting family, even more primitive than this one, so-called bicentric family. So let's look at the bicentric family. And what is a bicentric family? Before we even look at Brocard, let's take these Pascal lines out of here. This is a family interscribed between two non-concentric circles. So you can actually think of these two concentric circles as defining a pencil of circles. And the two zero radius circles in this pencil are shown here as the two limiting points, L1 and L2. So, of course, this is an n equals 6 family, and I can pick a particular n equals 6 family that I want to play with. Okay, and then now look at what's happening in terms of the Pascal lines of this family. And right here you see that there's a beautiful phenomenon taking place. It looks like rays want to congregate once again near L1, although not in a sort of a stable manner. They're actually expanding and contracting around L1. And there seem to be a few rays that always go through L1. And I'm saying rays, I mean Pascal lines, right? And there's also a bunch of Pascal lines that are going through a vertical line. So when I say vertical, I mean perpendicular to the OI axis of my bicentrics, going through L2. So I can see here that there is a there's a thicker line, and that becomes apparent. There's a thicker line going through L2 and perpendicular to OI, where rays will occasionally congregate. So I don't see immediately an enormous amount of structure here, but there seem to be these attractors, right? There's an attractor in L1 and there's an attractor in L2. Let's see if we're getting a similar phenomenon that we're getting before, where one or more Pascal lines were actually marking points of tangents. So it looks like there's one Pascal line here is going through this tangency point. There's another Pascal line here going through this tangency point, and there should be other ones going through the other tangency point. So I have individual Pascal lines marking my tangency points with a caustic. That's pretty nice. And I'm sure that this one here is going to have more structure than meets the eye. We can just observe this thing for a while and let this information sink. So the idea here is much is known about Pascal lines in general for any hexagon. And the question that we might be raising here is there any specific structure that arises when these hexagons are now constrained to be certain families of Poncelet polygons? Let's look at the last family, so-called MacBeath family. And this is a family interscribed, also circle inscribed, interscribed between a circle and an ellipse whereby one of its foci is a circumcenter. Okay, now let's observe that and see if we can spot out any. Let's play a little bit with this aspect ratio so we can make this thing more comfortable to the eye. Yeah, it looks like there is an attractor here, right? There's a bunch of lines congregating here. Some of them always passing through this point and others that want to contract and expand about this point. And I'm seeing some structure here. There's a particular straight line that looks like an axis. Okay, so this could be some axis related to this family. You can see that this axis never disappears. What am I talking about here? I'm talking about this line over here. So this is a vertical line that is a stationary Pascal line. And we were seeing a stationary Pascal line in the bicentric case, this one over here. You can see going through L2. And we saw a stationary vertical line in the Brocard or harmonic case as well. And this one was actually the strongest of all stationary lines. I can tell that there's a bunch of Pascal lines going through it. So I think that out of the three, the harmonics, the ones you're looking at right now, the bicentrics and the MacBeath, I think this one probably will reveal the most structure, and this needs to be studied. Okay guys, I'll see you in the next video.